Hello, welcome back. So today we're going to talk about logistic regression, another system of machine learning. So the objective for this section will be to talk about what is a logistic regression, when can we use a logistic regression versus a linear regression or a k nearest neighbor system or a cluster system. So and then we're going to see the machine learning perspective and the application of the logistic regression. So the definition of a logistic regression is a supervised learning algorithm for predicting the probability of data belonging to each class. So notice that in this here, we're mentioning to determine what it belongs to each class. What it belongs to each class. So if we see here, right, very important. So what this means is that logistic regression is a classification type algorithm. Okay, so in other words, it's going to determine whether a picture is of an animal is a dog or not a dog. It can determine is it going to rain or not rain. So that's what it means to be a classification. So that's a discrete type. We mentioned other systems like the linear regression before, which is a continuous uh, regression, right? So in other words, this will determine, instead of determining whether it's going to rain or not, a linear regression, because that's a continuous, will determine the temperature. You can determine so let's say that we're talking about temperature, right? You can determine the temperature that is going to be on that day, or you can determine how much is it going to rain, like how many inches of water is going to rain. So that's a value that we can determine by a continuous value. So that's a linear regression. So logistic regression, even though regression means continuous, it is referred to in this case the regression being continuous in the fact that it's going to determine a continuous probability. We'll mention that a little bit more in depth in a few seconds. But I want to emphasize that again, regression can be misleading in this case, right? It is a logistic regression, but regression, even though it means continuous, this is not going to determine a continuous prediction. It's going to determine a discrete prediction. Again, discrete means that it's either one category or another category, right? Not one class versus another one. So it's either one or the other one. There's no continuous value. There's no a continuous value between them. Again, a linear regression is a continuous prediction where you can actually have any value within the range. Again, if we want to think about the weather, right? A weather can use a logistic regression to determine if it's going to rain or not rain, or it could use a linear regression to determine what will be the temperature or how many inches of water will rain, right? So that's a continuous values, right? Temperature is continuous, and then also the number of inches is going to rain. That's also a continuous value, right? So I just wanted to make sure that you guys understand that there's a difference in here. Even though it's a regression, it's not to predict a continuous value, but instead it is a classification. Okay. All right. So we also saw a different type of classification, right? And that was the k nearest neighbor system. So that one is also to classify a prediction between one versus the other one. Okay. Again, and I even here in the notes are saying, despite the name, logistic regression is used as a classification algorithm. It uses a regression to classify the data. So the graph for a logistic regression is not going to be a linear line like the linear regression. Instead, it's going to have a curve, which is going to be in the form of a S. So a logistic function has the shape of an S. As you can see here, you can see this shape of an S in the right side. So a logistic regression will be represented by a graph that looks like an S shape. The y value represents the probability of belonging to that class 1, which means 100% on the top, and 0% on the bottom. So here's the classification. So either it is going to be a cat or not a cat. So when we see this right here, if your value of whatever value in the bottom part we get somewhere that is, in this case, let me change the color to blue. So let's say that you have a value, one of your values in your features in the end calculated to be a -4. You see that your probability is going to be somewhere around 0.5, 0.05 probability. That is, sorry, a 5% probability that is going to be of a not a cat. So anything that falls below this threshold line, so in this case we can label the halfway line, the 50%, to be our threshold line. Anything that lands within a percentage less than 50% will be classified as a not a cat. Anything that probability lands above the 50% will be categorized as a cat. Now, what this value represents, the S represents, will be the probability that is the correct answer. That is a cat. That is a not a cat. So, for example, here at -2, we have a probability that if your value is -2, that the probability that is not a cat, that is a cat, is going to be 0.1. So that means that the probability of being a cat is going to be very close to not a cat, right? So like 90%. Okay. So we use the probability to be able to determine the chances that is a one classification versus the other one. So of course, as you get closer to the top, right? So if your value output becomes a 2, then you figure out that your classification will be a cat because it is above your threshold, and this value will determine the probability that it was the correct answer, which in this case it is 90%. So it comes with a 90% probability that it was a cat. Okay, so doesn't matter where you land. If you land right here, automatically you're gonna be considered a cat. If you land somewhere even close to the threshold, you're gonna be considered not a cat. So that's the threshold line. So either you're one or the other one. But we use the probability to determine. We use the graph to be able to determine the probability of getting the right solution. Okay. So that's the differences. That's why it was called regression, because it provides a probability. It gives you another way of verifying that your classification, a prediction classification, is correct. All right, let's move on to the next one. So here are many different examples of how we can use a logistic regression. So again, a logistic regression is a versatile and simple approach adopted from statistics. So many of you have seen this approach in statistics. However, it can be a powerful tool for predicting the likelihood that a patient has a disease or not based on the symptoms and test results. So you can have a disease or not based on the symptoms that they have and the test results. So again, a classification. Either you have the disease or not. We can use it for email spam or not, right? Is it either a email spam or not, based on its content and sender. Again, one versus the other one, a classification. An image of a cat or a dog based on the aspect of the image. So we can determine either a cat or a dog. Again, classification. Customer will buy a product based on how long they spend on the product webpage. Again, it is a classification. Either they're gonna buy it or not buy it. Okay. So here is a little more in-depth example of somebody who is going to buy or not buy. So here, let's say that we gather all the information about a person spending time in a website and determining whether they're gonna buy the item or not. So for example, here. So here we have that person. So in the left side, we categorize the probability. It's going to represent the probability of being classified as 0 or not, class 0 or class 1, won't buy or will buy. In the bottom part represents the time that this customer spent on that website. So in here, we're saying that if the customer spends 1 minute on the website, then the probability that they're gonna buy the item will be practically almost zero. If they spend 2 minutes on the website, then the probability that they will buy the item, they will buy something, will be almost zero as well. If they spend 3 minutes, again, close to zero. If they spend 4 minutes, close to zero. If they spend 6 minutes, close to zero. If they spend 7 minutes, close to zero. And then if they spend 8 minutes, it's kind of getting a little bit higher, right? So it's almost like 5%. And if they spend 9 minutes, it's gonna get close to 10% that they will buy something. And notice that there's a item here, a data that is up here, right? When somebody spends 6 minutes, they actually bought the item. So those guys are called outliers. So these guys, they were not consistent with the data that we provided. So in this case, they spent 10 minutes and they bought the item. So they're still they're still gonna be influencing the shape of your graph and how much is it going to shift or extend, but they're still considered part of the graph. So sometimes they're referred to as outliers. And again, here, this is the threshold. So any value that falls within the bottom probability, then is going to be considered that they won't buy it. Okay, so anything that lands over here, it will be considered automatically that they won't buy the item. Anything that lands above that threshold, in other words, beyond 11 minutes, it will be considered that they're gonna buy the item, right? Okay, so that's the idea. But not only does it tell you that, but it tells you also with what probability is that correct. So for example, 13, the person spent 13 minutes and the shape, right, the graph landed at this point, which gives us a probability of close to 90% that they will buy the item. So this is saying that if they spend 13 minutes on the website, the probability of them buying the item will be almost close to 90%. So it is going to be classified as predicted that they will buy the item with a probability of 90% being correct. That's what it means. That's how we can interpret the logistic regression. Okay? And then why is it harder to accurately predict class if the probability gets closer to 50, right? So if we get our class closer to 50, right? So this kind of get a little bit harder to be able to determine if it's going to be one versus the other one because it's really, really close to 50%. So there's going to be some ambiguity in the data distribution. There's going to be sensitivity to some outliers. We talked about those outliers, right? These guys are called outliers. There's going to be some imbalanced data and non-linear relationships. And then move on to the next one. So training logistic regression models. The core of training a logistic regression model is an interactive optimization algorithm. Interactive optimization is like tuning a violin. So we're going to have to tune our logistic regression graph depending on the data we are processing. We're using to train our logistic regression model. So let me say it again. So like a violin, you have to tune to make the perfect sound. We're going to have to tune our logistic regression with data to be able to make sure that makes the best prediction. Okay, so we mentioned that, let me go back a little bit. We mentioned that the logistic regression is a supervised learning model or algorithm. Right? That's too big. It's a supervised learning algorithm. Remember, a supervised learning algorithm is like a teacher, where we are, for example, imagine that you have a teacher that's teaching a child that what is an apple, right? So it's showing them based on data, hey, this is an apple. And based on that learning, right, the next time you give that child or you show the child an apple, they will recognize that that was an apple because that's how it was trained to do. So in other words, a supervised learning will provide the correct answer to the data. Okay, so remember that a supervised learning algorithm will provide the right answer to the data. So it's like a teacher teaching a child what is the correct answer when labeling an apple. Okay, now why am I mentioning that? Because when we tune when we're tuning our logistic regression, we're using the correct answer and the data to be able to tune our logistic regression model. Okay, so we're tuning it. We're making it sure that it's going to predict the best answer. Okay. Logistic regression models. Training a logistic regression model is about fitting a logistic function to the training data. Again, our goal is to tune the logistic regression algorithm using the data and the correct answer. So right here, we could have started with a very, very far graph. So imagine that we could have started something like this, where it's very spread out. And then little by little, we're tuning this graph a little bit better, right? With the more data we give them, the more data we provide it with the correct answer, it gets tuned better and better and better. So that we can see this new graph showing a much better tune logistic regression that makes a better prediction, that has a better result in probability for the different data types that we test on. Okay, so that's what it means to tune it, is that we're going to be shifting that graph until we get the best logistic regression graph that predicts the best with the best answers. Okay, so it tries out one logistic function at a time. So we did the red one, and then representing a potential probability distribution. So we make calculations. We calculate the likelihood that training data will come from that distribution, and then we make adjustments. Continuously test different logistic functions to maximize the likelihood that the training data coming from that distribution. So we keep testing our data, our logistic regression is determining how good the prediction is, and we keep doing it until we have the best logistic regression possible. Okay, so that's what it means to train the data, to tune the logistic regression. So imagine that you're training your violin, right? When we mean training your logistic regression model, is what we mean with tuning your violin to make sure that it plays the best music. So in this case, the same thing. We're going to tune our logistic regression so that it can make the best prediction, right? So we're gonna train our logistic regression to make the best prediction. That's what it means, okay? All right, we'll move on. So now, how does it do it, right? Now, this is not a mathematical class, and to be able to understand the mathematical part of it will be a much more advanced course in mathematics, probability, and probably even in a graduate course in mathematics. So that's not the point of this course. But in the same sense, I'm going to explain to you guys the function that represents the logistic regression, right? Our goal is not to fully understand this equation and how it's derived, but for us to understand where the training changes are being performed, okay? So during the training phase, logistic regression aims to find an optimal values for the coefficients and intercepts that best fit the training data. So here's the key part. We're looking for the best coefficients, the best optimal values, coefficient and y-intercept that best fit the training data. What does that mean? What do we mean with those ones? When we were talking about the A1, the coefficient A1, A2, A3, A4, A5, so on, all the way to AN, depending on how many features your data has. And then we're going to have a y-intercept. So depending on how many features, the number of features determines the number of coefficients. So the more features we have, the more coefficients we will have to train. Right? We need to train those coefficients. Right? We need to train those all coefficients. So we have, if we have n features, we're gonna have n coefficients. So that means we're gonna have A1, A2, A3, A4, so on, all the way to AN. That's what it means. That's what it means that we're training our data. We're practically modifying, finding the optimal values for this A1, A2, A3, AN, and as well as our y-intercept. Now, often we call this A1, A2, A3 in a different system. We call them the weight value, and we sometimes call them the weight value. Okay. Now, sometimes, but right now we're just gonna call them coefficients. So, like for example, in deep learning, we call them weight values. In this, we call we call them the bias number. Okay, but so you might see it like that. Maybe in some books, or some people might reference them as weight values and the bias values. But right now, we're just gonna call them coefficients and y-intercept. So this is going to be your coefficients. And this is going to be your y-intercept. Okay, so the way we train the data, the more data we're plugging in and we're training it, right? Remember, this is a supervised learning. That means that we're going to provide the data the correct answer, and using that information, we're going to train the model. In other words, we're going to modify our A1, A2, and so on, so that we can best fit the data. By considering the coefficients and intercepts, logistic regression enables us to estimate the probability of belonging to a particular class, which forms the foundation of 4 classification tests. Again, based on this function, we're going to be able to calculate the prediction, right? The probability of choosing the right classification. It's either one versus the other one. Okay. So here again, I explain a little more in depth. What does it mean? So the x1 is you're going to represent the data. The a1 represents the coefficients, but the x1, x2, x3, and x4 is going to determine how many is going to be represented by your features data. Okay. Remember, I said at the top before that the number of features determines the number of coefficients. The reason is because every coefficient will have an x value. Okay, so the coefficients and x-intercepts are parameters that you will model learns to use for your training. Remember, in the k nearest neighbor, we talked about hyperparameters, right? In this case, we're not talking about hyperparameters, but instead we're talking about parameters. A little bit different. So in this case, in a linear regression and a logistic regression, we're going to have parameters, not hyperparameters. The hyperparameters are usually dependent on the model that will create a different perspective of the system. In here, there is always going to be the same system. So we're just going to train your coefficients A1, A2, and A3 to fit the model. So again, that's the idea. This sum is called the log odds and has the deeper mathematical meaning. However, we do not need to explore this to understand logistic regression for now. A1, A2, A3, and A4, so on, represents the coefficient associated with the predictor variables x1, x2, x3, and x4, and so on. B represents the intercepts or the bias term. 1, 2, 3, 4, 5, and so on are called the features. Like I said before, in the marketing example, there was only time. There was only time for the when we were doing the prediction of somebody buying or not buying. Right, we only had one feature. In that case, the feature was time. It was represented by time. So depending on how much time they spend on the website, we were able to predict whether they're gonna buy it or not. So in that case, there was only one feature. They are inputs to the model. So the features are the inputs to the model. So we're gonna be putting data to the model and give them the label. In other words, the correct answer, and from that they're gonna be able to learn from it. Now what we're gonna do is we're gonna talk about the differences between logistic regression, the k-nearest neighbor, and the linear regression. So we talked about the linear regression before. Logistic and linear regression both create a continuous equation as models. We mentioned that in the beginning. This is what makes the regression an algorithm. So again, they both form a continuous function. That's why they're both called regressions. But one is used for classification. That is the logistic, and the linear is used for continuous predictions. So let's go and see other differences. So logistic regression is used for classification. It is good for fast predictions, inferences, getting the probability of a classes. Not good for nonlinear relationships between features and labels. A k-nearest neighbor is used for performing classifications. Good for fast training, nonlinear relationships between features and labels. Not good for inference, getting predictions quickly. And then the linear regression performs regression classification. Regression predictions, and they can do fast precision inference. Not good for nonlinear relationships between features and labels. But they use these equations in fundamentally different ways. Specifically, the logistic regression's output can be mathematically proven to represent the probability of a class. On the other hand, linear regression's output could never be interpreted as a probability. Okay, so let me talk about that. So notice that the linear regression, so if I were to draw a linear regression here on this equation, on this graph, it will look something like this. It could look something like this. So this could look a linear regression. Now, as you can see, this linear regression, this line would never be able to represent the probability. Why? Because probability usually is ranged between 0 and 1. And you cannot have the probability of more than 1. So this could keep going forever and say that you have the probability of 1,000. So this is going to say that depending on the time that somebody spent on the website, that they could have a 1,000 probability of buying the item. That does not make any sense. 1,000 probability does not make any sense. So as you can see, the linear regression cannot be used to represent a probability value. It can be used to predict what will be in the stock market, what will be the price of the stock. But it's not gonna be able to determine if you should buy it or not. Right? A classification will help you determine. A logistic regression, you can use it to determine if you should buy the stock or sell the stock. Right? We can use it for that, but we cannot use the classification to determine what the price will be. Instead, we use the linear regression to determine the price of the stock. Again, I just wanted to show you guys, remind you guys the differences between logistic regression and linear regression. Logistic regression captures the idea of probability much more accurately than the linear regression. For starters, its output is always between 0 and 1, which is what the probability should be. A linear regression output goes on forever. It could predict something meaningless like 1,000% probability. That does not make any sense, 1,000 probability. And then we can think of a logistic regression as basically the bending linear model into the S shape of a property. So you can think about having if this is your XY plane, and then you had your linear regression, right? Imagine that you take that line and you stretch it. You, instead of putting it all the way to zero to keep going to infinity, instead you make it equal to 0, and then you make this, and then this, where this is equal to 1. So you see, this is still going to represent a probability between 0 and 1. But again, it doesn't fit the data as good as a logistic regression. So instead, we should have it better look like this. Now, this system is called a sigmoid. We will see some of these examples in the future in as a system as a system for the deep learning machine. But anyways, so you can think of the linear line being stretched to form the sigmoid, so that it can better fit the data. One of the advantages, one of the biggest problems in AI is that sometimes it's really hard to be able to see the logic behind the prediction of the machine learning model. So to be able to interpret and explain why the machine made that prediction is fundamental. The reason why is because, let's say that you're using a machine learning algorithm to be able to determine if a person should go to jail or not. Now, this is something very, very important, right? I mean, they could spend the rest of their life or whatever in jail. So what we want to do is we want to make sure to understand why the computer or the machine made the prediction. If we can't explain it, then how do we know it is correct, right? So that is one of the most important factors in studies in the machine learning, is how can we interpret the prediction? How can we interpret and explain the prediction based on the model? And the ability to understand and explain how the machine learning model arrives at this prediction or decision is super important. The S-shaped curve is crucial for the algorithm to work properly, ensuring that the predicted probabilities are interpretable and can be used to make the informed decision. Okay, so that's good. Logistic regression's output probabilities are easily interpretable, allowing stakeholders to understand the reasons behind the model's prediction. So again, this is explainable, artificial intelligence friendly. So we're gonna see the next. So the logistic regression coefficients provide a clear mapping between a predictor variable and their impact on the predictor model probability. So it's based on this probability function that represents the logistic regression graph. So again, logistic regression is an explainable, AI-friendly algorithm. In other words, the interpretability of the logistic regression aligns with the principles of explainable AI. It means that we can interpret and explain what the model prediction was made. So logistic regression versus KNN marketing example, they're both classification type algorithms. In this case, the K nearest neighbor and the logistic regression both capture the buying behavior well for a short and long times, but the KNN does not capture the tougher, the middle points very well here. So it doesn't really quite capture the prediction when it's in the middle, like the 50-50%. And remember that the K nearest neighbor system is based on how many neighbors did you want to use to be able to predict the to be able to label that classification, the data. So remember that the KN is kind of like the saying that tell me with whom you're hanging out, and I'm gonna know who you are. This is kind of like that KN nearest neighbor. It's like whoever you have mostly around you, depending on the size of your K, then that's who you're gonna be able to. So that's who you're gonna represent. So in this case, it doesn't really make capture the middle ones, the ones that are really close to both classifications really well as the other one. So here it is an example of a probability of a tumor malignancy and a tumor size. So here we're using the tumor size to be able to determine if the person is going to have the probability of having a tumor malignant. So in here, the size of 2.1 over 6, which is about 15% or something around 16%. So like 2.16 size of a tumor will be used to be able to determine if it is a malignant or a tumor size. So here we're using the threshold doesn't have to be at 50%. You can determine what that threshold would be for your model. Okay, so here this is determining with the probability if it is a malignant tumor or not. In contrast, KNN has no underlying model. It just memorizes the training data. It does not assume by any specific functional form for the decision boundary, so it can work in non-linear regressions. Some of the pros and cons of using a logistic regression. A pro is very efficient for training and even more for testing. Allows both predictions and inference. Outputs probabilities for classes, which is more nuanced than many other classification models. So practically none of the other model systems will give you a probability on how well the prediction was made. They will provide other tools like precision, precision, accuracy, F1 score. They're all gonna be used, and they are ROC as well, to be able to well, not test, but score our prediction. It also one of the pros is that they're very easy to use, easy to update model with the new data. The cons is that it technically only works for linearly separable data. We'll talk about what that means, which is not usually the case in the real world. Can require feature selection, feature engineering, and regulation. Feature selection means that you have to select what are the proper. Let's say you're given a lot of data, and each data is giving you information about a specific feature. A feature would be, for example, let's say that you want to predict if you want to buy a house or not buy a house. Some of the features for that data that you're gonna want to collect, right, will be for the price of the. Where is this? Will be the size. So some of the features that you might label features that you might categorize would be price, right? So you're gonna collect the price of the houses, the square footage, the number of bedrooms, maybe the number of restrooms. Interest rate. So some of those are some of the features, some of the data you want to collect to help you determine if you want to buy the house, if you're gonna buy a house or not. So these guys are the features. Now, some of those features might not make any difference in the prediction. So we need to make sure that we select the proper features. That's what it's called. That's what it means with feature selection. Feature engineering refers to normalizing some of the data. In other words, let's say in some cases, let's say that the price of the house, which could be in hundreds of thousands, in comparison to the square footage or the number of restrooms or the number of bedrooms, will be very, very, very different. So we don't want to we don't want that the price of the house influence too much on the determining whether you're gonna buy the house or not. So we don't want them to outshine the values of the other one. So we want to normalize the data, and that is called feature engineering, modifying your features values. And then there's also regulations. Some of the cons will be risk of overfitting data, particularly with too many features and not enough data. So you could come into the, but that comes with every single system. You're always afraid of overfitting, so you have to be careful of not overfitting. So you have to be able to select the proper features and feature engineering. It can also be sensitive to outliers. So we saw that this was very sensitive to outliers. Next one. So again, we were talking about very efficient for training and even more for testing. So we can see that the logistic regression training skills with features and data points, testing skills with features, memory use with features, decay, and it's a constant with the training skills with and the testing cells with features and data points, memory use, features and data points. Linear regression depends on the more than features and data points. The testing scales with features and the memory used for features. Allows us to both allows for both predictions and inference. So it allows us to be able to make a prediction for using our data, and an inference. Inference means that you use logical data or logical reasoning to be able to make a conclusion. So in logistic regression, we use logical thinking to be able to make our predictions. And so here, for example, we can see that this coefficient is bigger, way bigger than the other ones. So that means that this coefficient here has a bigger impact on the probability of on your prediction than any of the other ones. And in here again, now we go to the bottom. Now this one in the bottom part will represent the least. Now it's going to be way smaller than the other ones, which means that we'll be having at least amount of influence on the prediction that your algorithm will make. Okay, let's move on to the next one. So when we were talking about linear separable, so this is what it means. Logistic regression assumes linearly. So linearly separable, it has to have linearly separable data so that it can be classified using one of the lines, straight or not. The machine learning models tends to find this data easier to fit. So for a linear regression model, we need to be able to have data that is linearly separable. So you can see here, we can separate this three data with a straight line. And if we're talking about a three-dimensional space, then we can separate it by a plane, and then a fourth dimension by, I don't know what would that be, but it would be a three dimension. So here you can see that this is not a linear separable data. It's much more combined, it's spread out. And so combining multiple logistic regression models can help get past this issue that is the beginning of the deep learning. So we can actually fix this problem by having multiple logistic regressions so that we can separate the data. And that will be sort of what we're going to talk about logistic regression, deep learning. We mentioned about feature selection again. Feature selection is important because the quality of the logistic regression predictions significantly drop when many unimportant features are introduced. So when we use features that do not make any impact on the predictions, that we're gonna be wasting time and wasting resources, and also might skew our data as well. Feature engineering particularly standardizes the importance because logistic regression inference can be can lose meaning otherwise. How do you compare two apples with 50 years of age? So that's the idea. That's the reason why it is important to have these inferences. Regulations so what we practically do for feature engineering, we probably standardize and normalize the data. Regulation it's an advanced topic what we explore to, another day. For now, just know that it is the way to encourage small coefficients in the model. This is done by default in sklearn. So logistic regression is not just a binomial classification; it's actually a multinomial regression, logistic regression. So we can do more than just classifying a dog versus a cat. We can actually classify multiple classes, and then the way we're gonna do it is by doing a permutation of each one. So when we want to be able to classify cat versus a dog versus a bunny, what we can do is we can determine that we can classify them. Oh, sorry, we can do a logistic regression for classifying it that is a cat versus not being a cat. In other words, cat versus being a cat, a dog, or a bunny. Or we can process another logistic regression algorithm to be able to label them as either a dog or cat and bunny. And how would this look like in a monomial model? So one model with an exponential. So imagine that this has n different features. So the way we're gonna do it is we're gonna calculate the value for the dog, the probability of the dog on the top over the probability of getting not a dog. And so that will probably allows us to be able to find the probability and label if it's going to be a class 0 or a class 1. 1 versus the rest OBR. Models in n-binary models that can each n-binary models that each determine the probability of belonging to each class or not. So we talked about that. So we can do a cat versus not being a cat, a dog versus not being a dog, and a rabbit versus not being a dog. So that's how we can actually extend the binary of the logistic regression to have multinomial classifications. So now that we know what a logistic regression means, how can we measure the precision of our prediction? Since logistic regression is used for classification, we can use the exact same evaluation matrix as we use for the k nearest neighbor. So we can use the confusion matrix, we can use the accuracy, precision, recall, and F1 score. Now, because logistic regression is also gives probability, there are several more advanced matrices one can use. More than just using the probability of the logistic regression. We can use the confusion matrix, the accuracy, or the precision, recall, and F1 score. So usually we use the probability in the logistic regression to determine what class does it belong to. So again, the confusion matrix again is made out of a 4-dimensional square, or not a 4-dimensional square, but a 2-dimensional square 2x2, where we have the predicted values and the actual values. So we can see here we have our predicted value. So we have, this is a true negative, this is a false negative, and true positive, meaning that only these guys were the correct answers. Okay. Sorry, I was just thinking. Okay, so I think, why is this too big? Anyways. Alright. So for the accuracy, we use the sum of the true negative and the true positive the probability of getting it correctly, true, positive, true, negative. That will be your probability of getting it right, and the probability in the whole probability of the rest. So practically we just add everything and we determine what was the probability of getting it right. So that's the probability of getting it right. Accuracy is the probability of getting it right. Then we have the precision. Precision will be the probability of getting it right, true, positive. So we have the probability of getting it right. And sorry, not that one. Sorry, not that one. Probability of getting it right from the actual solution. So sorry, I choose the wrong one. Sorry. So it's actually getting it right from the making the right prediction. So what is the probability of getting it right, getting the right decision? So this is making a probability, choosing the probability of making the right decision. Okay, I have had made the right choice, true, positive. So that's the precision. The recall will be the probability of getting the right choice from the actual solution. So it's actually finding the probability of making the right choice, getting the right choice, the right answer from the actual solution. And the last one is the F1 score. The F1 score, what it does is a way to combine the precision and the recall to better accurately determine the accuracy of your prediction without any imbalanced data. Now, there's another way to be able to determine this accuracy, and that is called use the receiver operating character. We call it the ROC curve. And what we do is we calculate the sensitivity percent divided by the true positive rate, and then we compare it to the false positive response. Sorry, rate. So we're practically making a comparison between the sensitivity. What is this? Making comparing the sensitivity percent. In other words, the probability of getting it right, the true positive divided by the total observed positives, and then divided by the false positives divided by the total observed negatives. So if we can compare those values, then we're going to be able to have a way to predict how good our prediction was made. The ROC allows us to observe how changes in the classification threshold affect the sensitivity and specify of the model. As the threshold shifts, the true values rate and false positive rate changes accordingly. Now, ideally, what we want to have is what we have on the left. The middle does not give us any prediction power, and then the worst case will be if we actually have the right side graph. So we want to have this left sort of upside down L on the top. This is going to be the best possible outcome that you get on your graph. This is this is not good, and this is the worst one. You don't want to have everything incorrect. So the applications, usually how it works is the application medical diagnose uses clinical data, puts it into the machine learning, and it makes it diagnose. Due to the use of the interpretability, logistic regression has been used to help the diagnose diseases such as diabetes, heart disease, and more. Because we can actually explain why the system made that prediction, we can actually use it for medical purposes. Another way we can actually use it is for credit scoring, to determine if they should loan if they should loan the money to the person or not. So that could be used for we can use logistic regression as a way for credit scoring. And then again, the steps to be able to implement a machine learning model is going to be the same as we have done it before for the linear regression and the k-nearest neighbor. The first thing we're going to do is load the data, decide whether the feature will be predictors, and which features will be you want to be the target, the y value. We want to split the data into training and testing data sets. It usually is 80% training, 20% testing. We're going to import the machine learning algorithm. Is it a linear regression, a k-nearest neighbor, or is it a logistic regression? We're going to set the model's parameters or hyperparameters depending on what kind of model or algorithm do you have. We're going to find the model in the training set, fit the model in the training set, in other words, tune it, and then test the model on the test data set. We're going to do some draw some visualization if we can do it, just so that we can see the predictions or some sort of way to interpret the data, and then evaluate the model's performance using the precision, the F1 score, accuracy, and so on. And then we're going to apply the model. Again, this is the same drawing, but same information, but with a different approach, right? So we want to use collect data, prepare data, model selection, training, validate and improve the model, and prediction. So this is practically the same standard format steps that you're going to follow when you actually use it. And again, how do we load the data? We have done it before. This is the same way we have done it before. So we use the library to be able to load that data set. Okay. So again, we're using this built-in data in Python to be able to do our project. So, but we can always extract information from another source like Kaggle, I think it's called Kaggle, or Irvine. You see Irvine usually has information with that. And then, so now what we have done, we have put all the data into this data set, and we're going to use the data set to be able to create our data frame. So we're going to grab the data, and then we're going to take for the columns will be the data sets with the features names, and then the target will be the target set dot target. So in Python, remember, we can actually leave it like that, and it will automatically do it for you. And again, this is the same thing we have done before. We want to separate our X training data, Y training data, X testing data, Y testing data. And again, Y represents the answer, the correct answer towards your data. And the way we're gonna split it up by using the model selection dot train has split to be able to separate what's going to represent our features and what's going to represent our target. We're going to use the test size as 20%. The test size will be 0.2, so that means that the 80% of the data will be for training and 20% will be for testing. Random state 42, when we use that concept, again, to remind you is that we want to fix the randomness. In other words, if you choose to run this program, it's going to give you different random numbers than it does to me. And so that's fine, but sometimes we want the other people to be able to compare a result and be able to let us know if this is right or not. So that's what I mean with that part. Linear regression model is going to be imported from the logistic regression. And then we're going to create our object of type logistic regression. And then we're going to fit our data and then we're going to make the predictions based on our X test. Then we're going to visualize our data. Our data visualization would be to interpret our findings to the committee, to your job, or whatever you want to do, or for fun. We can use the classification report to be able to do some other types of evaluating the predictions. We can import this ROC curve. So from the scalar matrix, import the ROC curve. The ROC curve is going to take two values, the Y test and the Y prediction probability, to be able to match them up. And then it's going to spit out two values, the FPR value and the TPR, which is from the graph that we showed you before, and then the threshold. The ROC, AU, ROC, AUC score is Y test, Y prediction, and so on. This is just to be able to evaluate our model, to just show the drawing of the ROC, and then the model prediction using the new X values, or the X training data. How do we use the model? Well, we can use it once we have trained the model and in other words fitted. We're going to use it to make a prediction from the X test. And then from that, we can actually create our predict probability. The predict probability is to be able to show to use it for other things. The predicted prob is a method in the sklearn logistic regression model that returns the predicted probabilities of each class label for a given pod. So this is going to give us it's going to do the job for us. But most of the time in Python, you don't have to create some of the tests that you're going to be able to use, that you're going to be able to find them useful. You can make your own classes and training data and training methods, but in this case, you're actually doing a pretty good job with that. And again, evaluations matrices, the accuracy, the precision, the recall, and the F1 score. The accuracy, not a reliable matrix to evaluate the best cancer classifiers, since the classes are in balance, and the cost of a false negative missing a cancer diagnosis is high. So remember, the accuracy was only meant to be able to determine the how good the prediction was made. The precision is important because the false positive misdiagnosing a benign tumor as a cancer can lead to unnecessary biopsy. So we want to make sure that we don't miss a cancer label, or that we give them an extra work to the people who already have or have turned in their work. The recall important because false negatives missing a cancer diagnosis can have serious consequences for patient health. And the F1 score balances the trade-off between the precisions and the recall, and given more comprehensive evaluation of the classifier performance. So this is a little more balanced score, where it takes the best of both the precision and the recall and the accuracy as well. As you can see here, we have a graph representing the different types of scores on our model. So we have the precision with the 98% and 96% being correct, a recall with a 93 to 99, and the F1 score to 95, 97, and support 43 to 71. So we can see here that maybe the 98 and the 97 are a little off. So that's probably why did you have to make this? Why you make the decision to be able to use this model? And again, the confusion matrix is one that we have used before. We use the confusion matrix with the Y test and the Y predictions, and the labels for the model classes that will be your features. The displacement will be equal to the confusion matrix display, and then we use the confusion matrix CM that we created in the model classes for display levels, and then we display the model. Okay, so that's the end of that lecture PowerPoint, and we'll see you guys on the implementation we're using Python.